Welcome to a presentation on rates of change in calculus. So a reminder about some things that hopefully you've seen before. Average rate of change can be looked at as a change in y. So I have f of b minus f of a, two different y values, and the related x values, b minus a. And that's just the slope between 2 points. If this is on a straight line, that's the slope of the line. If this is 2 points on a curve, then I have the slope of a secant line between those 2 points. We can use that idea of average rate of change to talk about instantaneous rate of change. So that's the rate of change at a particular point on a curve. Now, it's hard to have a rate of change if you have these 2 points sitting on top of each other. So it's a little bit different idea to think about. But we have a rate of change at a particular instant. And that's what we call the derivative. So f prime of a, I just let b slip on top of a, and then I get the slope of a tangent line on a curve. So we've looked at that already in calculus. Picture we've seen before, we have some curve f of x, we have some value x called a, we have another one called b, and then that generates 2 points on the curve, f of b and f of a. Sometimes we like to talk about them as the space between them is called h, or delta x, change in x. So b could be thought of as a plus h. So those are the same y value up here. From that, I can find the tangent line. So I can take that secant line, scoot b over so it sits on top of a, and so I turn the secant line between those 2 points into a tangent line, this dotted line. So what's the slope at that point right there? And it turns out there's a relationship between the change in y and the change in x, and that's related to the tangent, the instantaneous rate of change. So if we know the change at that instant, we can scoot over h here and use that slope to project us up over here, and that's going to approximately give us f of b here. Right? So the tangent line slope projects us up as we slide over, and we end up at this other point. Now notice in this case, the tangent line value at b is a little bit higher than the actual function value. If it was curving a different way, it could be a little bit lower. It just kind of depends. But that change in y, here I have it equal to, it's approximately equal to f prime of a times whatever h jump we take. So looking at that in terms of an equation, f prime of a, if I replace the b with an a plus h in both places, then I get this traditional formula for looking for a derivative. So this is the limit definition of a derivative. If I just skip the limit for a minute and say, well, let's just h be a little number, then the derivative is approximately equal to the tangent. The tangent slope is approximately equal to the secant slope, if h is small enough. If that's the case, I can multiply this h over to the other side, and then I get the change in y. Right? That's my delta y is going to be approximately equal to h times the slope. So that slope and that horizontal distance give us a vertical distance together, because slope is rise over run. I can take that a step further and say that this new y value, y2, the y2, is approximately equal to, this would be my y1, plus my slope. And again, the slope here, that's like our m, came from the change in x. And the change in x, well, you could think of that as just x minus x1, right? Distance between two x values. And this formula should look familiar to you right here. This is the point slope form of a line. So all I'm doing is taking the idea of a derivative, relating it to the point slope form of a line, and this gives us the idea of projecting a tangent line to approximate function values. Up here, I have a change in y. Change in y, often when we take the limit, that turns into dy. In math and physics, we call that a differential. In economics and business, we call it a margin. Okay. So we're going to play around with using this stuff in different contexts, this idea of a rate of change. So first I want to look at physics examples. So in physics, if f of x is a position function and x is time, then f prime of x dy dx, my claim is that's velocity, because then I want to have a change in position here over a change in time. Miles per hour, for example. Often, though, in physics, we use meters for distance and seconds for time. So in this case, dy dx would be measured in meters per second. Putting this into action. Suppose I throw a ball up in the air. I don't throw it too hard, but a little bit. And let's say it goes about 7 meters up. It's about 20 feet. Then my claim is that the height function, I throw it straight up in the air, it comes straight back down into my hand, is going to be equal to negative 4.9 t squared plus 10t plus 2. And this is assuming when I threw it up, I reached up a little bit, so that's about 2 meters up in the air. It left my hand at about 10 meters per second, and this is related to the force due to gravity. Gravity pulls down at about 9.8 meters per second per second. Gravity causes acceleration. Acceleration changes velocity. So acceleration is a change in meters per second, hence meters per second per second. So some questions I want to answer about this particular height equation here is what's the maximum height that we'll get to? That's an algebra problem. At what time does that happen? Algebra problem. What is the average speed from the peak to the ground? That's sort of an algebra problem too. What is the speed when it hits the ground? That's a calculus problem. So we're going to just play around with that. So taking this into a new screen, I have h of t equals negative 4.9 t squared plus 10t plus 2. And to find the maximum, that's going to happen at the vertex, because this is a parabola. And the vertex always happens when, let's see, we're using t not x, when t is equal to negative b over 2a. So here I'm going to get a negative 10 over 2 times negative 4.9, which is going to be negative over negative is a positive. 2 goes into 10 5 times, 5 over 4.9, and then we can approximate that on the calculator in a second. So that's the time we reach the maximum height. To get the actual height, I have to plug that number into my function, and out will pop the maximum height. So whipping out a calculator, let's do that. I'm going to scoot over to Desmos here. So h of, and here I have to use an x instead of a t, equals negative 4.9 x squared plus 10x plus 2. There's my parabola. And Desmos very kindly actually gives me those two numbers, but I'm going to confirm those calculations. I'm going to call t equal to my negative b over 2a. So that I found to be 5 over 4.9. And that's about 1.02. And if I click back on that point over there, I can see, yeah, Desmos says 1.02. And now if I find the height at that particular time, so I can just plug in t, because Desmos thinks t is 1.02, I get a maximum height of about 7.1. And if I go back to that function, Desmos says, yeah, about 7.1 is the maximum height. So that was my estimate when I threw my ball up in the air, how far it went. So I got that first part. So I found that the maximum height is approximately wavy equals sign 7.1 meters. And the time that it happens is about 1.02 seconds. All right, so that's the answer to part A. For part B, I want to know what is the average speed from the peak to the ground. So I'm assuming that's the second part of the journey. So the peak happened at about the point 1.02 comma 7.1. And next I need to figure out where it hits the ground. So the ground happens to be h equals 0. So I just set this equal to 0 and solve. So negative 4.9 t squared plus 10t plus 2 equals 0. It's unlikely this factors, so the quadratic formula is one way to attack it. So t equals negative b plus or minus the square root of b squared, 100, minus 4 times a times c. Oops, ran out of room there. Thought that might happen. So that's 4.9 times 2, all over 2a. So that would be negative 9.8. And there's really not too much point in cleaning that up because it's not a nice number. And I can confirm with the GeoGebra here. So let's see, we've got fraction, negative 10, plus, we'll do them separately, the square root of 100 minus 4 times negative 4.9. And you could have adjusted the signs there if you wanted to. Oops. Times 2 all over negative 9.8 is one of them. And I have an error there somewhere. I think I need times maybe. There we go. And then I've got the other one, fraction. And that's a negative number, so that's not the one I want. That's before I threw it. Plus the square root, 100 minus 4 times 4.9 times 2. Whoa, extra symbol, and we can change that to plus here because we're subtracting a negative over negative 9.8. And oops, oh, I forgot to do the minus. Plus was above, minus is this one. And then I get about 2.22 seconds. And so if I check with Desmos, Desmos says, yeah, about 2.224. All right. So that's the peak. My point at the ground now is 0, 2.22 if I go to 2 decimal places. And this was 7.10 to 2 decimal places. You could use more if you like. So then that means the average speed is just the distance, speed, change in distance over change in time. So my distance, I started off at 7.1 meters up, and I went down to 0. Change in time was, did I state that backwards? Let's see. Oh, I stated this one backwards. Oops. Something's wrong there. All right, the time is 2.22, and the height is 0 there. All right, that looks better. So then I went from 1.02 seconds to 2.22 seconds. So a little arithmetic, that's 7.1 over negative 1.2. And we can compare that here, or again, we're finding just the distance between these 2 points. And I could do that with function notation too and get a similar answer. So function notation version would be fraction. I want h of 2.22 gets me down to the ground minus h of 1.02 when I was at the peak divided by 2.22 minus 1.02. And I get negative 5.876. Compare that to the 7.1 divided by negative 1.2. And they're slightly different. Oh, rounding error is probably the case there. Yeah, it must be. All right, so they're in the ballpark, which is good. So I'm getting about to the nearest, let's see, what are we measuring here? Meter per second, negative 5.9. Just not ready for that one yet. So it looks like the average speed is about negative 5.9 meters per second. So that's the average speed from top to bottom. Now, if you look at the graph of this thing, and we zoom in on it a little bit, got this way, maybe too much. The slope over here is not quite as steep as the slope down here. So that's an interesting thing to consider. It's steeper down there. So we need to find the slope equation. So I'm going to sneak in here, and I'm going to call this d for derivative at x. And I'm going to use our formulas. Our shortcut formulas, the power rule is bring that power down and reduce it by 1. So I'm going to get negative 4.9 times 2, which is negative 9.8 x plus 10. So that right there is the derivative formula for this function. So this is my velocity. Maybe that's what I should have called it. Instead of d, it's called d for velocity. And what we should see here is that at the top here, I had a positive speed going up and a negative speed coming down. And so between positive and negative must be 0. So the slope should be 0 at the top, which was at 1.02 seconds approximately. And so the velocity equation tells me that, which is kind of cool. If I want to know what's the velocity at about 2.224 or 2.22, I can just ask the velocity equation that. What is the velocity at about 2.22 seconds? And it says that it's a negative 11.756 approximately. So maybe I could call it negative 11.8. And that was another question I was asked. What's the actual velocity when it hits the ground? Actual velocity at ground. So we calculated that it hit the ground at t equals about 2.22 seconds. So then we plug that into our formula, and we get approximately negative 11.8 meters per second. So it's moving a little slower at the top. It actually has that brief pause at the top where it's kind of still, because we went from a positive speed going up to a negative speed coming down. And again, between positive and negative, you got to hit 0. All right, so that is derivatives, rates of change applied to physics. I'm going to do one more physics problem and move on to a problem related to business. So here I have another one. I have a particle moving along a straight line. Its position at time t is given by this equation right here. So it's moving on a straight line. It's speeding up, it's slowing down. Maybe it's going, let's assume it's moving left to right, right to left kind of action. And the default direction, let's call that positive to make this easy to deal with. Actually, let's go up and down. Suppose moving up is positive and moving down is negative, and default direction is moving up. So we're going to answer some questions. We're going to figure out speed at different times of this thing and acceleration. So let's find those. So this is, again, the position equation. So the velocity equation is equal to the derivative of the position equation. And that would be 3 times 2, 6, drop the power by 1, squared, minus 2 times 24, so that would be 48, drop that power by 1, t, plus, that's t to the first, slope is 42. The power rule says multiply 1 by 42 and then reduce the power by 1. T to the 0 is 1, so it would be just a 42 there. That's the velocity equation. Acceleration equation, call that a of t, that is the derivative of the velocity equation, which would be the second derivative of the position equation. And it's really hard to do 2 derivatives immediately in your head, so you take one derivative and then take the derivative of that. So 2 times 6 is 12t minus 48. So this would be the acceleration equation. So for example, I could find the velocity at time 1 second. So that would be 6 minus 48 plus 42. So let's see, negative 48 plus 6 is negative 42, plus 42 is 0. It comes to a standstill at velocity equals 1. What was happening before that? What's happening after that? Acceleration at that moment would be 12 times 1 minus 48, which is going to be a negative 36. So from a speed of 0, it's going to decelerate, okay, is what we have here. We're going to get head in the opposite direction. So we're going to start being forced to move down at t equals 1. Well, what I'd like to do is kind of figure out when it's going forward and when is it going backward. All right. So, or when is it going up and when is it going down? Question mark. When down. So to do that, we got to kind of play around with this. So we know that it gets a standstill at 1. It has a 0. If I want to find other zeros of this, that's going to separate the when it's going up from the when it's going down. I should solve the equation s prime of t equals 0. So that's going to give me 6t squared minus 48t plus 42. And looks like 6 goes into all of those. So 6 goes into 48, what, 8 times? 6 goes into 42 7 times. And yeah, this factors. 6 times t minus 1 times t minus 7. So this tells me that, switch colors, when t equals 1, velocity is 0. Oops, wrong symbol there. 1, velocity is 0. And when t equals 7, velocity is 0. Just kind of check what's happening in between here. So for example, a nice number in between would be 2. What's the velocity at 2? Velocity at 1 is 0. Velocity at 7 is 0. If we plug in 2 to our velocity equation up there, let's see, v of 2 is going to be 6 times 4 is 24. 48 times 2 would be what, minus 96, and then plus 42. So what's that give me? Negative 72. Combine that with the 42. Oops. We're going to get what? 0, 3, negative 30. Is that right? So the velocity is negative in between here. Negative velocity. And so given that this is a continuous function and there's no extra zeros, it's probably going to go positive velocity, negative velocity, positive velocity. So I'm just going to map that out on a number line for fun. Important number is t equals 1. Another important number is t equals 7. The velocity, s prime, which is the velocity, it's negative in between here. And then I believe it's going to be positive on that side. We can plug in a number to test. And it's going to be positive on that side. So that means the position, it's going up here, reaches a peak, then it's coming down in this region, reaches a bottom area, and then it's going to start going up again. So let's find out how far it goes up, how far it goes down, how far it goes up again. And then let's say 1, 7, let's say 16 is out here. Let's find out how far it travels up to 16. So total distance. And you might say, oh, total distance, that should just be s of 16 minus s of 0. Problem with that is it goes up and down in between, so I miss out on some oscillation if I just do that. So that's not going to help me. What I need to do is consider the absolute value of distances and when it changes. So what do I need to know? I need to know the position initial. I need to know the position at 1. I need to know the position at 7. Oops, we're using S for position. And I need to know the position, I did it again, position at 16. So Desmos to the rescue. Get a new screen for that. And remind me of my function. 2t cubed, 24t squared, 42. So S of t, x, use x, is equal to 2x raised to the third minus 24x squared plus 42x. And so we should see some up-down motion. So I'm going to make a table and replace y1 with s of x1. Let's plug in some numbers. So I need the position at 0. Well, that's 0. I need the position after 1 second. That's 20. Position after 7 seconds, negative 196. And the position after, what did I say, 16 seconds. So I have 20, negative 196, 2,720. So for my positions, we go from 0 all the way over to 20. From 20, we drop down to negative 196. And then from there, we fly up over to 2,720. So each of these distances then, well, from here to here is 20. Now, here I'm above the axis, and then I have to scoot below the axis. So that distance is going to be 20 minus negative 196, which is really 20 plus negative 196, which is going to give me, what, 216 would be the distance traveled there. And then here I have to get from negative 196 all the way up there. And so that's going to be 2,720 minus a negative 196, which means I'm adding these guys and I don't need a calculator. What do we get there? We get 6, 9, 10, 11, carry the 1, 7, 8, 9, 2,916. So these are the distances this particle traveled up and then down and then up again. So the total distance would be the sum of all of those. So that's going to be, what, 6 and 6 is 12, carry the 1, 1, 2, 3, 4, 5, if I'm doing my arithmetic right, 9, 10, 11, and 1 and 2 is 3. So it looks like the total distance is 3,152, and I can't remember if this was feet or meters, but that looks like the total distance traveled here. We can double check on the graph. I'm going to have to adjust my graph to see some things. I need to get, let's see, I'm going to zoom. Let's see, for x, we can go from 0 over to, we'll go a little past 16, we'll go to 18. And then for y, we should go from, say, negative 200 up to maybe 3,000. So we can see all the stuff that's happening here. So we'll scoot over a little to negative 2 and close. So points of interest from the table, we start at 0 and we rise up to 20. From 20, we have to drop down to 196, which is a drop of 216. And then we have to go from 196, so like below sea level, to above sea level. So 2720 plus 196. And then we combine all of those to get the total distance. Up, down, up again. Okay, not too bad. Calculus helps us figure that out. Beautiful. Next. Business. Marginal revenue is the change in revenue per unit change in production. So technically what that looks like is we have some production level A, we bump production up by 1, and we look at the change of revenue as we have that from that higher production to the lower production. If you consider back to those equations we were playing around with from average rate of change over here, here I have my A plus 1, and then here I have F prime times 1, because I'm letting H be 1 for marginal revenue. Because marginal revenue, again, is the change in revenue per unit change in production. So we're letting H be 1 for that. So we get this nice relationship that the margin of revenue is approximately equal to the derivative of revenue evaluated at the current production level. That's what we have here. So here we're given a cost in producing X units of stuffed alligator toys is given by this cost function. And again, marginal revenue, marginal cost, it's all the same idea. So replace an R with a C over there. for cost, and we're looking at 1,000 units. So one way to calculate this without calculus would just be to find the cost of 1,001 units and subtract the cost of 1,000 units. And that's one way we can get marginal cost. The other way we can get marginal cost is to find C prime of X and then plug in our value. And in this case, we're going to plug in 1,000. So to take the derivative of this, use the power rule. It's going to give me 0.002 times the X value I want, which is 1,000. Plus here, derivative of 8x is just 8, and derivative of 5,000 is 0. So I get, this is what, tens, hundreds, thousandths, so 2 thousandths times 1,000 is 2, so I believe I get 10 for the marginal revenue. And so that's change in cost per, in this case, toy. So $10 per toy is the change in cost at 1,000 units per unit. Double checking the other way, I could plug that formula in to Desmos. So entering our cost function, we have 0.001 x squared plus 8x plus 5,000. And then I could just calculate what is C of 1,001 minus C of 1,000. Oops, that's not a minus. And I get it's about 10.01. If I take the derivative of that and find the marginal cost at X, that would be 2 times 1,000, which would be 2 thousandths. The sign would be a good idea there, times X plus 8. And so the marginal revenue in comparison at 1,000 units would be 10. So you can see that the marginal revenue is close to the rate of the instantaneous rate of change. But technically, marginal revenue is just a difference between two revenue values. But often it's easier if you have an equation to play around with the derivative to estimate that. All right, that's some applications of rates of change in calculus to areas of the world, tracking the position of a moving object and looking at revenue, cost and marginal cost. Have fun, do good math. I'll see you later.